Right, so it's being recorded now. So this 24B is on supercomputer, which is called Param Himalaya. Many of you have been using it recently. Many of you would want to use it, and some of you will want to understand a few things which are not very clear. So let's have this session. So this session will have a lot of things that I'll discuss, mostly very briefly. I'll talk about introduction, I'll discuss how to log into the system, then I'll talk about the scheduler, which is SLURM on this one, unlike PBS, which was on the HPC cluster. We'll do some interactive jobs just to play around with things. I'll talk about squeue, sinfo, scontrol commands, which are used to check the details about queues, partition, queues, the nodes available, and so on, the jobs running, and so on. I'll give you an OpenMP and OpenMP as well as MPI demo. We learn how to copy stuff back from the cluster once the results are generated. We'll talk about modules, which is not available on the HPC cluster, which is something which is extremely useful. We'll talk about something called SPACK. We'll discuss batch jobs, because most of the stuff I'll discuss is through interactive jobs, but ultimately for a cluster environment we need to send in batch jobs. And towards the end I'll talk about how job priority is calculated when you are sending jobs for execution, because many people are frustrated that my job used to run, it was running very easily through the queue some time ago, but today it's just sitting in the queue. I don't know why. Others' jobs are running. So we'll talk about job priorities as well. And I'll also discuss something about virtual environments, because Conda is also available here by default. So there's an amazing manual for Param Himalaya. Those who have read it will find this session mostly redundant, because everything that I discuss here is also available in the manual, but I thought of having this session for completion. Let's look at this, let's look at the manual first. It's an amazing resource. So you go to Insight on the intranet website called Insight. On the left hand side in quick links there is something called Param Himalaya. You click it, you get two links, one is for user creation and the other is for user manual. So you click the manual and you get this 92-page manual which has almost all the details that I will be discussing today. So again, as I said last time, this session is also being recorded. So don't make me stand up and ask you to leave. Okay, so if you really want to speak up or talk, do it outside the class. There is also this link called DCS IIT Mandi /Param Himalaya. If you click this, it takes you to this digital and communication services link on Param Himalaya. The interesting part is at the bottom where you have GPU and CPU utilization. So let's click CPU utilization, and it gives you a detailed report that has been created about the utilization of these services. So this is between 26th of Feb 24 to 26th, so it's a 1 month report. So you can see how many jobs were submitted, how many were successful, how many nodes were allocated, how much time was run. So this is done through a software called C-Chakshu, which was developed at CDAC. It's a nice dashboarding tool. So it gives you utilization of the cluster, how much has been reserved, sitting idle, downtime, and so on. It tells you users utilization, so it gives some details about that. If there is one user using it heavily, you will have that there. Some kind of jobs submitted, accounts, sometimes you have paid accounts which get extra priority. So how much was that, how much was internal, how much was external. So this is IIT Mandi using 61% of the cluster. Earlier this was very small, so now we have more people using it. Number of jobs submitted and so on. So there's plenty of stuff, fun stuff that you, if you like analytics, you will really enjoy this. And there's a similar one for GPUs as well. Okay, so this gives you an idea as to how popular the cluster is in the last 1 month. Anyway, so that's analytics. So what is Param Himalaya? So Param Himalaya has Intel Xeon Cascade Lake processors, which are these two types of processors. We also have NVIDIA Tesla V100 GPU cards, very powerful cards. The interconnect is InfiniBand, So what that means is that the connection between the nodes is through 200 gigabits per second. So that's really fast interconnect. Okay. So then MPI jobs are really good on this one. The file system is a parallel file system made through Lustre, and the peak capacity of this is around 850 teraflops. So that's a lot of computing power it has under the hood. The architecture is, it has 2 master nodes, 4 login nodes, 4 service nodes, and a total of 156 compute nodes. So compute nodes is where the computation will happen. Login nodes is where you log into the cluster. That's for the users to log in, compile stuff, copy stuff, and so on. So unlike our HPC, our HPC has 2 login nodes. One is N199 and one is N65. This has 4 login nodes. It has 2 master nodes. So master node is something which sort of when you start the cluster, it loads all the components. So it's very important to have the master nodes running all the time. So they also do a lot of health monitoring, making sure all the other nodes are working properly. Then you also have service nodes, which whose role is to manage like schedulers and so on. So this is the setup that we have. Out of the compute nodes, we have 107 CPU nodes, 10 GPU nodes, and 39 high memory nodes. High memory is 768 gigabytes per node. So that's a lot of memory for one node. So in case you want to run a heavy memory heavy job like learning lights or lamps or molecular dynamics or DEM kind of codes, you will want to go for high memory nodes, because the more number of particles in the larger n size you have, you will also need higher amount of memory to keep them in the RAM. So typically a CPU node has 48 cores in it with so it's a dual socket. Each socket has one processor has 24 cores in it. The clock speed is 2.9 gigahertz with a memory of 192 gigabytes for a standard CPU node. For higher memory node, as I said, it has 768 gigabytes, but the other things are very similar. So this is the architecture. Let's talk about it. It's very interesting to have a look at the architecture. So let's look at these lines now. So the green one is 1 gig Ethernet. That's typically what you get in your hostel rooms or these Ethernet cables that you have that are connected to your machines. This is 1 gigabits per second. Then the bottommost one, which is the brown one, is InfiniBand. That's a patented technology by Mellanox, which is in this case 200 gigabits per second. It's very fast. So 1G versus 200G, that's the difference we're talking about, 200 times faster than standard Ethernet. We also have a 10G interconnect, the yellow one, and there's an IPMI which is mainly used for management. It's some interconnect used for management, not for transferring data. Data isn't like the data for cluster, it's mostly for transferring information about health and so on. So the architecture looks like this. So at the bottom right you see a primary storage. So this is the storage drives which store all the information of the disks. You have 2 master nodes. Well, actually we have 4 service nodes, and then they're connected to each other. You have a firewall as well, and then there's a login node, login nodes that users log into through a firewall, and then we have compute nodes which include CPU nodes, GPU nodes, and high memory nodes, and so on. Okay. Then we have this switch structure which has switches for IPMI, which is for management communication. It has L1 InfiniBand, L2 InfiniBand, and so on. Okay. Even I don't understand, I'm not a networks person, I don't understand these things in a lot of detail, although I know how to connect switches because I've been involved with HPC for some time. So this can get quite complex when you manage the facility, but this architecture sort of gives you an idea as to how the clusters working. I showed you a picture in the beginning. So this is how this is pretty much it, right? These 3 almirahs. That's it. That's the whole cluster. So it looks quite small, and even though here it's not just nodes in this, it also has a cooling system. So the way the cooling system works is the cooling system cools the whole rack. So it's not a room which is getting cooled and then you have a machine sitting here. No. So the cooling fluid. So there is a lot of stuff happening below the ground as well. So below the ground we have pipes and all running with heat exchangers. So there is some internal oil that flows through the system that cools the machines. So the machines are liquid cooled, not air cooled. And then this oil which is running through the machines, cooling them, exchanges heat with water which is running in pipes at the bottom of the floor, which goes out into large dry coolers, chillers like you see cooling towers, etc. They have big pumps sitting. So the cooling system is around 250 kilowatts, which is 60 tons. So you have the idea of people who are from hot regions, they know ACs, right? So you have 1.5 tons of AC. That's typically what people have at home. So 1.5 ton means 1.5 refrigeration ton. So this cooling system is 60 RTs that's cooling the system, but this is much more efficient. So that way it's much more efficient than your standard AC. So effectively it's actually much more cooling power only for these 3 Almiras, which have all the hardware sitting in them. So there's a lot of energy required just for cooling the system. But that's not it. It has 8 kilowatts of pump. It has precision air conditioners. So what I talked about was only for the compute nodes. On the left hand side on this black rack, you have the master nodes, login nodes and service nodes. So they are not cooled by this ATOS cooling racks. So they require room cooling. So for them we have 46 ton big AC, so that's a huge AC as compared to 1.5 tons that you typically see. It has a 400 kilowatt or 500 kVA UPS. Okay. Then it has a similar amount of, so if there's a power outage, it can work for a few minutes on the UPS, and then a diesel generator kicks in, which is those who live in South Campus would have seen a large pipe going up. Okay. So that's to dissipate the smoke from the generator quite high up so that people cannot smell it. So that's a chimney for the generator. That generator again is 400 kilowatts, and there are numerous sensors like fire sensor, rodent protection, CCTVs, and there's also a building management system. So that manages, so there's a room which has big televisions with some lights and all like you see in movies. It has the lights keep blinking if there's an error somewhere, so there are lots of sensors involved. So it's highly automated, that facility that we have. Okay. So it's a state of the art facility that we have, and there are very few supercomputers in the country. So we are lucky to have a supercomputer at IIT Mandi. Well, enough about boasting about the facility. So let's talk about how to use it. So you have to log into Param Himalaya, and many people have been frustrated with this CAPTCHA. How many people have used Param Himalaya and are facing issues with CAPTCHA? Okay, well you can get rid of it. You can use passwordless login. Okay, we discussed with HPC cluster that you have to generate a key pair, and you upload that on the cluster. So once you do that, it's exactly the same instructions. You generate key versus public key pair, basically key lock pair, and then you copy the public key onto the .ssh/authorized keys folder on Param Himalaya. You already have one that's available there for login to the nodes. You can put one more or as many as you want depending on how many systems you want to access it from. And after that, all you have to do is you have to say SSH followed by your Param Himalaya username @paramhimalaya.itmandi.residence, and you have to put the port details as well, and that should authenticate you from that key that you have on your machine and not take you to the CAPTCHA or ask for a password for that matter. Okay, so let's try it out. And how many have been frustrated with typing this long username @ So now it will not ask me for a CAPTCHA. Well, it is not happy with it, so Control C, try it again. This time it will not ask me. So okay, it depends on the mood, but there are times it might ask me, but mostly it does not. Okay, so it has logged me onto the cluster. Before that, I don't like typing this whole thing, so I have created my bash rc. So I have set an alias where this whole command is there, and I can use ph login or whatever you want there. So here what that means is I can simply type ph login on my local machine, and that automatically means expands to the whole SSH etc. Okay, so once you set up the alias, then you simply can type whatever you want, a short You can even have just 1 or 2 letters, and that should log you in. Okay, so this is just to make our lives easier. Well, once that is done, when you log into the cluster, you get some welcome message as we just received here. You can see that there is a welcome message. So I printed that and pasted on the slides. It tells you details of the hardware available, 107 CPU nodes and so on. It tells you about some standard commands that we will be discussing today anyways. It talks to you about, tells you about modules and some file retention policy. Do read about the retention policy. It says if you do not access a file for 3 months that's been sitting in the scratch, it will automatically get deleted. There is a script running. If you do not access if you have not visited or accessed a file for 3 months, they assume that you don't need it, and they keep cleaning it regularly. Okay. So SLURM stands for Simple Linux Utility for blah blah blah. It basically is resource management or scheduler that is very similar in functionality to PBS, that PBS torque that we had on the HPC cluster locally. So in this case, and most of the big clusters or biggest clusters available in the world, they use SLURM only, okay, nowadays. Well, the first thing you will want to do is you want to run something which is interactive. So let's try it out. Well, let's have a look at the command. So you say srun instead of q sub, then you provide the number of nodes you want, and then you provide the number of cores per node. So in our cluster we always go for 1 node because we said that the interconnect is very slow. It's basically using a 10G interconnect between nodes, whereas this supercomputer uses 200G interconnect. So this is much faster. So in this case we can actually go for more than 1 nodes, but for now we will start with 1 node and 1 task per node, which is basically 1 core. So 1 node is like 1 hardware, and task per node is the number of cores you want. So you have a total of 48 cores maximum available per node, and then you have to specify the time. So I want to run for a total of 15 minutes in this case, and then -i stands for interactive, and this PTI bash basically says that you bring open a bash terminal on the compute node so that I can do something with it. So once you do this, it should take you from this login node, one of the 4 login nodes, to one of the compute nodes, which is denoted using Cn with a number. Okay. So let's try it out. I may have typed the srun command in the past, so I can just use that. So srun 1 node, 1 task per node, 15 minutes, that's it. Okay. So let's run it. So now you can see it takes me to Cn026, which is exactly the same as the one I got last time when I prepared the slides. So this is I am on the compute node now. So now I can do things like running codes and so on. Before that, let's do a man srun. Well, let's end this job first. Let's do a man srun because srun is available on the login node. So now you can see lots of options available here. So please make sure you go through these at least once in your lifetime so that you know what options are available to you to do. This is much more than what q sub allowed, so it's worth trying this out, and even the cluster has more options available with it. Okay, so please go through it. Again, today I don't want to do that. I just want to give you the options or the features available. Then once you run the let's say have a job running, you will want to see like a qstat. So in this case you have something called sq, where did my job go and so on. So you type sq, and then that basically gives you the job details of everyone who's running the jobs right now. Okay, good enough. Just for fun, let's have a look at who's running what. So this is partition, basically means your queue. So on SLURM, instead of saying queue name, it has a partition name, so it uses the word partition. So there are different partitions available. You can see CPU, GPU, standard are 3 that I can see. Then there is a name, which is basically the name of the job name whichever the user has given, user, which is username, status, which is whether the job is running or it's waiting in the queue, and so on. R stands for running. So you can see that the job has been running for 2 days, 7 hours, 3 minutes and 20 seconds. Okay, this is basically time. It tells you the nodes, how many nodes have they taken. So this job is running on 10 nodes. Next is node list. So what node list they are using? So this one's taking CN 6 to 9, 31 to 32, 65 to 67 and 77. So all this information is available for you to look at, and your job will be somewhere here as well. Okay. You can also do an SQ minus L, which is basically minus L stands for, again you can have a look at the manual for SQ, which gives you lots of options available. I particularly will be showing you minus L, which is for long. So it has more details. So this time it also gives you some more information, or information in more detail about, actually it's very similar, right? It just instead of saying R or P, it's saying running or pending. So it's basically elongated fields. It also gives you a time limit. So mostly by default the jobs are allowed for 4 days. So you can see this 4 basically means 4 days. And if you want more than 4, then you have to request with them, and then so this is Ashish, you are running this job. So did you have to request for increase more than 4 days? No. Okay. So by default it is 4 days. If you do not specify any time, if you specify time less and more than that, I didn't know that you can go for more than 4 days. You can go for up to 7 days here. Okay. So you can figure these things out. This one's actually running for well, sent for 7 days, and this one is actually run for 7 days and being sent for 10 days. Okay, so this is a useful command to use, especially if your job's waiting in the queue. And again, it's fun to look at other people's jobs, but I would really want to look at my job. So for that you use --me, and then you press enter. In my case, I'm not running anything right now, so it does not show anything. If my job's running or waiting in the queue, etc., it shows the jobs for me. There is also a formatted output in case you want a particular kind of output. You can use this, that can give you more information or information in more detail. So you can read about these things on the internet or the manual in case you want the output with some other extra features about the jobs or so on. Okay. The other two commands which are useful are sinfo and scontrol. So let's look at sinfo first. So sinfo tells us about the information about the queues or the partitions available. So it says that you have standard GPU, CPU and also HM, which is high memory nodes. So you can specify these partitions in when you send the job for running. If you don't specify anything, like we did not specify anything, so it goes to standard by default. And that tells you that this range of things, which is either down means it's not running, it's not working, and so on. Reserve means it's being reserved for someone, and so on. Okay, so this has some detail. You can do a -s, which is I think the short form. In concisely tells you that you have these queues without details of what nodes are doing what. You can also do an sinfo -l for long, which then has slightly more amount of information as to. So basically, if you want to look at what queues are available, you will use sinfo. I can actually write sinfo -N, and that gives me details of all the nodes. Okay, so now I can look at what node is doing what. So CN001 is compute node 1, it's in partition standard, it's also on CPU. So a node can be mapped to multiple queues or partitions. It has 48 CPUs or cores, then it tells you about the memory and so on and so on. So this gives you detail of all the nodes in case you want to send your job or you want to figure out what hardware is available and running right now. There is an even more detailed command called scontrol. So scontrol gives you more control. So if I say scontrol show node and then CN001, so this gives me more information about the node. I will not read it through, but you can literally keep changing if you want to figure out what this node is about, so on. So you can get that information. Again, scontrol also gives you information about partition. So, let's say partition, and then I want to say CPU. So, now it gives me information about the CPU partition or the CPU queue that is available in more detail. Now, you would also, if your job is running, let's say, or in queue, you will want sometimes to know more information about a job. So, now if you say scontrol show job with a job ID, it gives you information about that job. But if you do not specify any job ID or partition ID or node ID, it gives you information about all the jobs in this case. So, it is very transparent. Okay. So, everybody's jobs are visible in terms of what the details are. So, you can see that this particular job ID has a particular job name, the user ID who wants to run it, and so on and so on. Okay. So, when was it submitted, how long has it been running, and so on, what resources have they either are they using or have they requested, and so on. And then like you had a queue del to delete a job, you have a scancel here to cancel a job. Okay, so this srun, which is for interactive run, is mostly required for testing the code. You won't use it for large jobs. Large jobs are sent in a batch mode, which is basically similar to queue when you send a job without interactive mode. And one more thing, if you have a privileged account, which means that you have been given, you have paid some money to CDAC for giving you a privileged account that you can do from projects. So, in that case, you get some extra privilege over the others. So, then you have to specify minus account equal to whatever account name has been given to you by them. So, if you use that, then your jobs will be put into the this account. Okay. In many clusters, you have to specify an account because there is nothing free, or if there is something free, they basically say that everybody gets 200 rupees worth of credit, and after that you have to keep adding money into your account. Okay. So, let us try something out very quickly. Now, those who have used the facility will, but this session, those who would want to learn how to use it now. So, let us run this srun, which is interactive run. I will use 8 tasks per node, basically 8 cores on one node. It is allocated that to me on CN026. Now, what I will do is, I already have this HPSC 2024, I copied that just to save time. So, let us go into that, let us go to codes, let us go to OpenMP, and we had a code called timings, which basically does a matrix multiply A times B, a total of I think 10 times, and then it shows us the CPU time as well as the elapsed time. So, let us compile it using Fortan. Okay, so this compiles. I think I modified this code slightly because typically when you run it, it will ask you for the number of threads as well as the size of n. So, what I have done is I have hard coded the size of n and the number of. So, let us run it using .out. Using OpenMP, how many threads? Let us say 2. So, n is 300 by default and it took 3 seconds of elapsed time, around 5.9, basically 6 seconds of CPU time. So, it works, the CPU time is double the elapsed time. Okay. So, if I ran it on one thread, it would have typically taken 6 seconds of elapsed time. So, one thread is taking 6 seconds, 2 is taking 3 seconds. Now, let us go to 4 threads. So, that should be 6 by 4. So, 1.5 seconds approximately good, and if I go to 8 threads, that takes only 0.8 seconds. Okay. So, good. So, things are working fine. I am happy with this thing. Now, I can send a batch job with larger n value and larger number of threads if I want. Is that clear? So, I won't do anything more than this on an interactive job. Now let us try this lecture 1 that we just tried on the cloud. So we go to the Fortran folder, lecture 1. So I already here, so I will do a make clean. If I do an ls minus l, so make clobber, sorry, make clobber will delete the output files as well. So now I only have the make file in the codes. So now let us do make plots. So it is doing the same thing, it is running on one thread, running on two threads, and then it will run the Python script. So again there was an error because I have to activate a virtual environment. So now if I, it's already generated the output, so it's simply plotting using Python. Okay. So you can see that contour.png and pcolor.png are available. So now I literally have to just copy. So this is basically how your code runs. You have the output files generated. Sometimes you will want to copy the output data and do post processing on your local machine. In this case we simply generated everything on the cluster, and now I simply have to copy these things from the cluster to my local machine using SCP. How to do that? Well, you will go here, you will say SCP, and then my username and whatever it is @paramhimalaya.ac.in, and then I have to specify the path, but I do not like wasting. So what I have done is I have made in the bash rc with something called a bash rc. Bash functions are available, you can actually generate that. So basically it runs this command scp -p, which is for port, my username @Param Himalaya, and then colon, and then you have the file path. So this file path is specified as an argument to this function, and then I want to copy it to /. So all I have to do is I have to type phscp, that will run this command, and then instead of file path it will take $1, which is whatever I specify after that space. So let us demonstrate that. So I have to say phscp, and then I have to specify the file path. I can literally get that using pwd. Copy this, paste it /contour.png. So that will run that complete command and copy the contour.png, and now I have the contour.png, which is copied just now 1919, and I can do display contour.png. Okay. Questions? Good. Modules. So there is something called modules available on this cluster. So let us clear things. I am still on the compute node, so let us exit from there. So my job is completed now. I can actually see sq -me, so there is nothing there, so my job has been completed. So modules are basically some things which modify the environment variable. They do not do anything particular, they just modify environment variables to make certain executables available, so that you do not get overwhelmed with too many executables. So let us check. So you say module avail, which is the available modules. So it will give you a list of available modules, and then you can use this command called, let us say I want to run MATLAB. So I see that there is a module called, yeah, so here. So you have a module MATLAB /r20, so 2021. So let us say module show and then MATLAB. So that should be enough, I do not have to specify the complete one. And then it says the module file, which is this is the module file that will get enabled if I enable the module. It gives me some more information about this module. So now I have to, what I have to do, let us do one thing, let us print the environment called path. So path is that variable that we have talked about long ago, that basically has all the paths which are enabled by default in the terminal. So this user local bin, whatever executables it has are available to me through this terminal, as well as all these as well. So let's load the module called MATLAB. Let's check. So I say module list. So it tells me that currently loaded module is MATLAB. Now if I do print env followed by path, you will see that the path has been modified. This thing home apps MATLAB bin has been prepended here. Okay. So that means that all this command module load did was it added this thing to the path. If you knew this path, you could literally have added it yourself if you want. Okay. Now what will happen is whatever is available in this bin folder is something you can type on the terminal. So now I can do module unload MATLAB, and if I do a module list this time it's gone, there is no module loaded. If I do a print env path, you can see the MATLAB thing is also gone. That is pretty much what modules are. There's nothing complicated there. There are some installed software in some paths. You simply have to expose that path to the path environment variable. You literally do not need to load module to use those software. SPACK. SPACK is another thing which is quite fancy. It's like apt-get somewhat. It basically allows you to download, build and install packages through this thing called SPACK, and you can even basically the commands are like you module load SPACK. So you load the utility called SPACK, then you can find modules, install them, list install you can find packages, install them, list them, load them, and then etc. etc. So you can figure it out what it is, but it is quite useful if you want to download or install packages, and you can have different versions of them also possible available. So here I will show you an MPI job. So let us do it in the interactive mode again. So this time we will take, well, let us take one only, that is okay. Why waste resources for demonstration? Let us do it for 4, because MPI will run, it does not care whether you are running on one node or multiple nodes. So it has allocated me the resources. So now I want to let us go to the HPSC codes MPI, and I will want to demonstrate the matrix norm 1 code. So for that I have to compile it first using MPI F90, but how do I get the compilers? So let us look at module avail, which is a list of modules available. This time I will use something called Intel compiler. So it says compiler Intel, this thing. So let us copy it, say module load, and this compiler. So this if I do a module list now, you can see it has been loaded. I can check which MPI F90. So MPI F90 is available. So MPI F90 followed by the code norm 1.F90. There is an a.out generated right now, and how do we run it? We say MPI exec minus n4 followed by /a.out. So it asks how many rows columns, let us say 100 rows and 50 columns. So this one required n calls less than numprox. So let us use matrix norm 2. So 100 rows, 50 columns. So now you can see it runs the code. It says process 2 received message with tag 2 and so on. So we discussed this code earlier. Okay. The whole idea for today is that it can run MPI jobs as well, and that is not too complicated here. All I need to do was load the compiler and run it. I am going a bit fast because I have to cover a few slides. Now once you are happy with these things, you want to set up a batch job. So batch job is where you just send the job for a run, it runs in the background and generates the result without you interactively connecting to the compute node. So it's very similar to QSub. So you have sbatch, you take the number of nodes, you take the number of tasks per node, the time required, job name, error file, output file, the queue name or the partition name, and then you cd to the present directory and then you run the command. That's it. Nothing complicated. Let us have a look. Let us exit from this. Okay, so I have scripts folder. which has this batch1.sh. So let's have a look at this batch1 script. It's the same script I showed you right now, okay, which is running a ./a.out, which is executable. It's already sitting in my directory. I don't remember what it is, but let's run it. So the way you send it is you say sbatch followed by the batch file. So once you do that, it gives you a job ID, and now I can do squeue --me. Oops. Seems that I was slower than the job. So it ran. Let me check the batch job. Okay, so this is the one that's being so the job ID was 553636. So that's this one. Okay, so this was that timings code. So it OpenMP with 4 threads. It did a multiply with n equal to 200, and it some time it took. So it took 1.8 seconds of CPU time and 0.4 seconds of elapsed time. Okay, so the job ran fine in the batch mode. So this is how you, and all these scripts are available in the user manual. So feel free to explore that. There are some other batch flags available in case you want to use GPU, you have some account, you want to force the code to a certain node, or in this case even emailing is enabled. So you can set your email address, you can have a mail type that in case the job runs or the job does not run or there is an error, you can specify when to send you an email, and you won't have to write a manual script that we did in HPC. Here things will hopefully work on the mail as well. So you will get an email when some things happen. I have never tried that, but I think it runs. Some other things, so make sure you have a look at this more about batch jobs chapter in the Param Himalaya manual. For OpenMP scripts, typically we will have to set this environment variable OMP num threads, because if that is available, then it will use the num threads from the script. You want to specify that in the code. Then for MPI, you will see that there are these environment variables called MPI fallback, MPI fabrics, and MPI debug. Scripts will have that. So fallback is basically, if your Intel compiler that you are using does not work, then it usually will fall back to some other compiler which is available. But if you say disable, then it will give an error if Intel compiler does not work. So that's just to make sure that the results are not unexpected. So if you disable it, then it will make sure it runs on the Intel compiler that you have specified. There's a fabrics here. So the fabrics is basically see, MPI jobs can run on shared memory as well as on distributed memory between nodes. So this tells that what sort of communication technology to use. So if you are running MPI on a shared technology on a shared single node, if you say this SHM, so that uses the shared memory. So that's basically faster communication, and this DAPL is for telling that you use InfiniBand. Okay, so if you have multiple different communications between nodes available, you use so if these things basically tell the compiler to use the so not compiler, basically it tells the cluster to use the fastest communication possible. So just use these options which are recommended by the architecture. Not specifying them or specifying a wrong one will basically, you might end up using a 10G connect when 200G connect is available. So make sure that you specify these properly. Debug is just for what sort of output verbosity you will get in the output. Some features also, you can have dependencies of one job over the other. You can do that. You can reserve nodes, you can have array jobs and so on. So make sure you read the manual properly. It tells you the quota available, what sort of retention policies are available, and how to run codes in the fastest manner possible. Now, many people have this problem with job priority. I want to show something to you through this command called sshare -a-l. Gives a lot of information. So let's filter that with my name. So I'll do a grep. So this only prints stuff about me. and then also let's try somebody, let's try Ashish. So this command has an output which looks like this. It's a very large output. Basically it will print information about all the users. So it has information where you have something called fair share, level FS, effective usage. So this tells you what sort of use, if you are using the cluster heavily, your usage will, effective usage will change. Okay. So let's look at these last three numbers: level FS, fair share, and effective usage. Okay. Let's look it for Ashish and let's look it for me. So you can see that this number is how heavily Ashish is using the cluster as compared to me. So what will happen is that his effective usage increases, and what will happen is as this number keeps increasing, if we both try to send a large job, my job will run faster than his or go into queue because he has been using. So automatically if you use the cluster more, your usage gets increased and changes the metric. So there's a formula here of job priority that will include that factor of the fair share factor here. Okay. So there are many factors. If the job has been sitting for a long time, its priority increases. If the job size is very large, its priority might decrease. So smaller jobs will run very quickly. There is a partition factor. Some partitions are have more priority than the others, and so on. So this formula sort of helps you understand, and there is a weight associated depending on. So the weight is set by the administrator, but these factors are dependent on you or your jobs or so on. So make sure that if your jobs are not running, don't misuse the cluster, which will automatically affect your priority as well. Conda is available. Those who have used it can use it here. So you simply have to do a Conda create environment, and then you can. So this allows you to use different versions of Python if you want to. So you can do a Conda create environment with some version. You can have another version, and then you can install whatever you want on it as well. Containers. So Singularity containers are also available here. So containers are very useful. Those who have used HPC may have used containers. If not, there's a link to this video that I recorded some time ago in a training for containers on HPC. But in principle, containers work on cluster as well. All you have to do is you have to either download a container. So containers are like images, like machine images on Amazon and so on. So these are you can download Docker images and convert that to Singularity images. You can basically Singularity Hub is like a repository where all the containers are given. You can download a basic Ubuntu 24.04 and then you can start building. So in this video I explain how to build your own container with different software. So once you make a container on your local machine, on your laptop for example, this is all the software installed that you want. So now that image can be copied to the cluster and you can launch the software using Singularity exec, then your image file name .sif, which is basically a few gigabytes big file, and then the command to run. Literally you have to create a container. So containers are like virtual machines, but they are much lighter and they are much faster. So Singularity containers work. So if you have been using containers, Singularity containers on the HPC, you can literally use them as it is on the Param Himalaya cluster as well. As I said, please acknowledge NSM for in your publications, thesis, reports. It helps spread the information about the technology to the world. Read about best practices, and in case you have issues, it also tells you how to raise a ticket through some link. So Ashish will demonstrate how to install. So we talked about containers, we talked about using our own, compiling our own code. But sometimes you have open source code like OpenFOAM, lamps, lights and so on, which is not installed in the clusters. How do you download, build the code and install it yourself on the cluster? Ashish will demonstrate that on Wednesday next week. Okay. So thank you very much, and hopefully you got something out of it. We'll meet on Wednesday and you will have a